Last topic of the unit, I want to talk about energy of charges in electric fields. I want to draw a couple diagrams, one from Physics 20, take you back to a little analogy that we're going to use to help us to understand the second diagram that is a new Physics 30 diagram. First one looks like this. You got a hill, and you got a little go-kart that's powered by gravity on the top of this hill. That go-kart has a speed, let's say, of 0 meters per second. Got a height of a hill of, let's say, let's make it 20 meters. The second diagram is going to be of parallel plates. Top plate we're going to make, let's make it positive. Bottom plate we're going to make it negative. We got a positive particle in between those plates near the top plate, and it's going to have an initial speed of 0 meters per second. There are gravitational field lines pointing downward, right, toward the center of the Earth. There are electric field lines pointing down from the top plate to the bottom plate. Make sense? All right. Tell me what happens to this go-kart at the top of this hill. Tiana, what happens to the go-kart at the top of this hill? Yeah? Well, there's a go-kart sitting at the top of a hill on a slope. What's going to happen to the go-kart? It's going to go down the hill. It's going to go down the hill. And as this car goes down the hill, it's going to lose what type of energy? It's going to lose potential energy, right? EP goes down. Gravitational potential energy decreases. What do you think is going to happen to this positively charged particle as it's exposed to this downward electric field? It's going to what? It's not going to get more negative or less positive. No, it's not going to change its charge any more than that car gets more car or less car. It's going to travel toward the negative. It's going to accelerate toward the negative, right? We got a force acting on this positively charged particle. We have force acting downwards because the force is with the field. It's a positive particle. The field is downward. The force is with the field. Now, as it accelerates down toward the negative plate, speeds up toward the negative plate, what kind of energy is this charged particle going to lose? Potential. If it speeds up, it must be losing potential. At the same time, what does this car gain? What does it gain? Kinetic energy, right. What kind of energy does this charge gain as it moves towards the negative plate? Kinetic energy, right? What doesn't change? What doesn't change through this whole thing as the car goes from the top of the hill down towards the bottom of the hill? Nolan, what doesn't change? Okay, the car itself, sure. Yes. Yeah. Yeah, gravity doesn't change. I'm thinking more in terms of energy, though. Matt? The total energy, yeah. The total energy doesn't change there. In other words, potential energy decreases, kinetic energy increases, but they increase, decrease proportionate to one another so that as one goes up, the other is going to go down. The total energy remains the same. That's exactly the same case over here when this charged particle is speeding up as well. As this charged particle speeds up, it loses potential energy, it gains kinetic energy, but the total energy is going to remain the same. Now, let's look at this first problem mathematically. This shouldn't be too hard for us because we've done this at nauseum in Physics 20, these roller coaster problems in Physics 20. We say that the initial energy is equal to the final energy because the total energy doesn't change, right? So whatever you have at the beginning is going to be equal to whatever you have at the end. What kind of energy do we have in this situation? That car at the top of the hill when it's moving at 0 meters per second, just before it begins to move down the hill. Kai, what kind of energy does it have there? Spencer, what kind of energy does it have when it's at the top of the hill? Potential, yeah. We're going to call that potential gravitational potential energy, or MGH. What kind does it have? Let's say I want to find the speed of it when it reaches the bottom here. What kind does it have when it reaches the bottom? It has kinetic energy, so we're going to make that 1/2 mv squared. Well, that's not unlike what we see over here. Why don't I just write it out again so it's not working the way that I want it to work. It's not unlike what we see over here. We'd say EI is equal to EF. And in fact, it's not technically MGH for potential energy, but we can think of it that way if we want. We can think of this charged particle speeding up as a car going down a hill. And we can think of it as MGH, initial, is equal to 1/2 mv squared, final. And then just replace MGH initial with the type of potential energy that we have. Does that make sense? Think of it the same way. Replace MGH with the type of energy that we have. Now, what kind of potential energy do we have? If you check your data sheet, there's an equation that says delta V is equal to delta E over Q. Potential difference is equal to change in energy over charge. Think about that. We defined potential difference already, right? As the difference in energy between two spots per unit charge. So if delta V is equal to delta E over Q, then V would be equal to E over Q. And therefore E would be equal to Q times V. So electric potential energy is not MGH, but rather it's Q times V. Big V. I'm going to put little tags on the top of that so that you see that it's not speed. It's a big V potential difference. Okay, if I'm typing that, you're not going to see those little tags, but you're going to be able to easily distinguish between a little v and big V if it's typewritten, right? When I write it on the board, I'll write it with the little tags so that you can tell the difference between a little v and big V. So this is a problem just like the first problem that we had, just like the problem that we had in Physics 20. Charged particle speeds up. That's like a car going down a hill. What kind of energy does the car have at the top of the hill? Potential. What energy does it have at the bottom of the hill? Kinetic energy. Do the same thing for the charge, except replace MGH with QV. Got it? All right. What if we change this up a little bit? What if this car at the top of the hill isn't at rest? What if it's moving at 10 meters per second? What kind of energy does the car have at the top of the hill now? Tevis, what kind does it have at the top of the hill now? Does it still have potential? It has kinetic, but it does still have potential because it has a height. Okay, so it has potential MGH, but now it's got kinetic energy as well. So we would say the initial potential and kinetic combined is equal to the final kinetic energy at the bottom of the hill. What if this charged particle is moving at the first plate at, let's say, 10 meters per second? What kind of energy does that charged particle have now? Well, it's like a car going down the hill. Picture it. Picture the car going down the hill. Ryan, are you picturing the car going down the hill? Yeah. Charged particle speeding up. Picturing the car going down the hill? Yeah. Really? Andrew, are you picturing the car going down the hill? Yeah. Really? What color is the car? Yeah? How many people in the car? It's just going on its own? Oh. And it's on fire. Okay. Can you see this? Yes. Is it like burning up a lot? No? A red car on fire. Maybe it's just like the red streaking that it looks like it's on fire. And Andrew says the car he's picturing doesn't even have insurance. All right, just let it go down the hill then. All right. So this car is going down the hill. Really, it's not a car. It's a charge, but we're picturing it as a car going down the hill. What kind of energy does this red car that's on fire with no insurance, it has no people in it, what kind of energy does it have when it's moving at 10 meters per second at the top of the hill? It's got both kinetic and potential energy, but it's not, because we're not really talking about a car, we're talking about a charge. It's not kinetic potential energy MGH, it's potential energy QV. The kinetic energy, though, is still the same kinetic energy, 1/2 mv squared. The energy at the bottom of the hill, or at the negative plate when it reaches the other side, is 1/2 mv squared. Same as the car would be when it reaches the bottom of the hill. How about this one? Well, now let's find not the speed of the car when it reaches the bottom of the hill. Let's find the speed of the car when it's halfway down the hill now. Okay, we're actually talking about the car now, the real car, not the charge, not this crazy car. It's in Andrew's imagination. What kind of energy does it have at the top of the hill? Same kind, right? Kinetic energy and potential energy. What kind does it have when it's gone halfway down the hill? What is it? It's got both of them, yeah. It's got kinetic energy because it's moving, but yet it's also got potential energy, mgh final, because it's still got a height. When it's got a height, it's got potential. When it's moving, it's got kinetic energy. Got it? Now, what would the initial height be? What would the initial height be in this problem? 20. What's the final height if we're talking halfway down? 10 meters. Got it? Let me introduce another thing over here. Not the distance between the plates, but rather, let's make the potential difference between the plates 20 volts. Okay, the potential difference, the difference in energy per coulomb between the top plate and the bottom plate is 20 volts. Okay, we want to find the speed of this particle when it's gone halfway across this gap, from halfway across the gap from one plate to the other here. What kind of energy does it have at the beginning? Again, we're picturing it as a car, a red car on fire going down a hill, no driver, no insurance. Kind does it have in the beginning? Potential and kinetic energy, except the potential energy isn't mgh potential, it's qv potential. What kind of energy does it have when it's gone halfway across? Well, we're picturing the car, right? We're not picturing the charge, picturing the car halfway down the hill. Halfway down the hill, that car has potential energy and mgh potential and kinetic energy. Same thing here with the charge, except it's not mgh potential, it's qv potential. We'll put the little tags there so that you know that it's not a speed, right? Q times the potential, the electric potential at that point. Okay, if the potential difference was 20 volts across the gap, what would we say my initial, not potential difference, my initial potential is here? We don't actually know. We don't actually know, but we can pretend we know and get away with pretending we know. Let's say that the potential here is 10, then the potential here would be 30. If the potential here is 50, the potential here is 70, right? The difference in potential is 20. The easiest way to do this is to say, and it works every time, is to say the potential here is 0. Got it? Just like we can define ground level over here wherever we want, we can define ground level over here wherever we want as well. So let's say the potential down at the bottom here is 0. What's the initial potential now? You were going to say this before. If this is 0, if the potential here is 0, then the initial potential would be, say it? 20. Good. What would the final potential be halfway across? 10. The potential is analogous to the height. Be careful with that. Some people want to make the distance between it analogous to the height. If it was 8 centimeters across, they want to make it, oh, the initial is 8 and the final is 4. No, we don't use the distances there. We use the potential that's analogous to the height. Does that make sense? Okay, one final thing here, okay? One final thing before we do an example here. Let's say that we're not speeding up as the car goes down a hill, but rather we're going to have a car at the bottom of the hill with an initial speed of, let's say, 20 meters per second. It's going to go up the hill, and we want to find out, let's say, how high the hill is. What would you do in this case? Caitlin? Yeah, flip them over, right? This is still EI is equal to EF. This time, though, it's kinetic energy at the beginning because there's a speed, and at the end of it, we'd have potential energy, right? Well, if a car is speeding up, it's potential to kinetic. If a car is slowing down, it's kinetic to potential. If the charged particle is speeding up, it's potential to kinetic. If the charged particle is slowing down, it's kinetic to potential. So we just say 1 FmV squared equals QVF if it's the charged particle. Does that make sense? Got it? So every time you see one of these problems now, every time you see one of these problems where a charged particle is speeding up, I want you to think of it as a car going down the hill. Think of it as a red, burning car with no passengers or no driver and no insurance going down the hill. Picture it. And then analyze it as that problem that you can see in your mind. and then just replace MGH with QV. I don't know about you, but I can't see in my mind a charged particle speeding up nearly as easy as I can see a red burning car going down a hill in my mind. So I picture the red burning car in my mind, and then I just replace MGH with QV wherever I need to. Does that make sense? Now, if the charged particle is slowing down, then we do the opposite, right? We think of it as a car going up a hill. We picture that red burning car with no driver and no insurance going up the hill. And then we analyze it in the same way as we analyze the car going up the hill, except we replace MGH with Q times V. Everywhere we had MGH becomes Q times V. All right? Let's take a look at example number 1. It says an electron is released at a speed of 1.0 times 10 to the 5 meters per second at a negatively charged plate and moves toward the positive plate. Okay, picture this now. See this. Is this charged particle going to speed up or slow down when it's released in this gap here? It's going to do something, right? It's going to accelerate, but it's going to speed up or slow down. The electron is released at a negatively charged plate where the electric field points upward. Which way is the force on this electron? Opposite to the field, right? The force is pointing downwards. This charged particle is going to speed up or slow down as it's moving toward that plate. It's going to speed up, right? Okay, now forget about that. Forget about the charged particle now. Picture it as a car, a red burning car, no driver, no passengers, no insurance, going down a hill. If this car starts at a certain speed at the top of the hill, what kind of energy does this car have at the top of the hill? Does it have kinetic energy? Picture the car. Can you picture it? Kai, can you picture it? See the car? Yeah? Does the car have kinetic energy when it's moving at the top of the hill? Yes. So we're going to say that the charged particle has kinetic energy when it's moving at the top plate as well. 1/2 mv squared. Does the car have potential energy? Taylor, does the car have potential energy at the top of the hill as it begins to go down? Yes. It has potential energy, MGH. The car does. The car has potential energy, MGH. Now, how fast is the electron moving when it's gone halfway across the gap? Okay, how fast is this car moving when it's gone halfway down the hill? Does it have kinetic energy now? No? Yes. How fast, does the car have, remember this red burning car, no driver, no passengers, no insurance, does this red burning car have, Megan, does this red burning car have potential energy halfway down the hill? Because there's still a height, right? So it's got potential energy, MGH. Well, now what I'm going to do is just replace MGHI with Q times initial potential, and I'm going to replace MGHF with Q times final potential. It's the same question. We think of it in the same way, except we replace MGH with QV. You don't have to be able to visualize the electron speeding up. You just have to be able to visualize this car speeding up. Now we sub in our numbers and we see what we get. The mass of the electron is 9.11 times 10 to the minus 31. VI here, it says, is 1 times 10 to the 5. The numbers in these questions tend to be a little bit crazier with exponents, but otherwise it's no harder than what you did in physics 20. Q for an electron is 1.6 times 10 to the minus 19. Remember, drop the sign of the charge in any equation. VI, we're going to say, is 20 volts. 1/2 of 9.11 times VF squared. That's what we're looking for, isn't it? Yeah, VF squared plus Q, which is 1.6 times 10 to the minus 19. What's the final potential here? It's like analogous to the final height. Sarah, what's the final potential of this? 20 volt initial, we go halfway across, 10 volts, right? All right, let's get some numbers here. On the left-hand side, let's say 0.5 times 9.11 times 10 to the minus 31 times 1 times 10 to the 5 squared. Let's add that to, let's use some brackets now, 1.6 times 10 to the minus 19 times 20. Okay, the left side now is 3.2 times 10 to the minus 18. Now, watch carefully. I'm going to subtract from that the 0.5 times 9.11. Half times 9.11 times 10 to the minus 31 times, oh, no, I'm not going to do that. I am not going to do that. Okay, my left-hand side again. I'm going to subtract from that this term, right? Because I'm looking for VF. So subtract 1.6 times 10 to the minus 19 times 10. Now I'm going to times that by 2, and I'm going to divide by 9.11. And I got my answer, right? Oops, what did I do there now? Let's try that again. 1.60455 times 10 to the minus 18, times it by 2, divide it by 9.11 times 10 to the minus 31. That should be better. And that's my answer, right? No, it can't have a speed that's bigger than 10 to the 8 meters per second. This is 10 to the 12. If I do what, Jack? If I square root it, then I end up with a number that seems more reasonable, 1.87 times 10 to the 6 meters per second. That's a pretty typical speed for a charged particle, 10 to the 5, 10 to the 6. It doesn't have to be 10 to the 5 or 10 to the 6. It doesn't have to be, but typically 10 to the 4, 10 to the 5, 10 to the 6. The last one, all the way to the negative plate. This is easier, right? This is easier now, because this is just 1/2 mvi squared plus qvi equals 1/2 mvf squared. What's the value of vi? 1 times 10 to the 5. What's the value of vi? The initial potential, 20 volts. And we're solving for vf. So the math ends up being a little bit easier now than it was in the last question. Your homework for the weekend, just when you thought you got out of it, it's worksheet number 9. Question number 1 to 4. It's not that many. It's not that much work for you over the weekend. Worksheet number 9, questions 1 to 4, please, for Monday.